Actually, it's my great pleasure to introduce Massimo here. We were PhD mates in 2003 in the Bari. Then he got his PhD and he moved to
Texas and
I know you very well. To Texas, then to MIT, then to Barcelona for 5 years. And then eventually he got his position in Gran Sasso Laboratory here in Italy. And he is very expert on this research field on which we are very active in this department, which is the QCD phase diagram. So today he will give a very nice, hopefully very nice, surely very nice, user-friendly introduction to this topic for the students. So since this is a colloquium, of course, feel free to ask questions anytime you want, also during the discussion, during the presentation. Okay, so let's welcome Matt.
Okay. It's a really great pleasure for me to be here in Catania, where there's a lot of friends of mine, and also there's a lot of vibrating activity on the phase diagram of QCD. And so please, ask questions, definitely, especially if you don't understand something. I may try to be as clear as possible. It's not an easy topic, okay, to explain. So I try to do my best to present it in such a way that basically from the background, you should understand everything. Anyway, there's also my email address here, so please send me an email. I'll be very happy to reply to your email. Okay, in due time, of course. So this is the Finnegan's Wake of James Joyce, 3 quarks for master mark. This is where these words were taken by Gell-Mann, and so it's nonsense, as in many stories written by James Joyce, and so Gell-Mann liked the sound, and which was meant to be K work, or in Italian we say the crasi between a question and mark. So it's something which at the beginning people were not understanding, were even doubting of the existence, and so Gell-Mann decided to take this weird name for that. It's a very nice story about why he decided to pick up this particular name for subatomic particles. So this is the outline. So I will start with some historical remarks, and then discuss properties of quark matter and possible phases of quark matter. And I will end up with an updated view of the QCD phase diagram. So let's start from the beginning, setting the units, which is MEV with the big M here, not to be confused with the MEV here. Distances are subatomic physics are in Fermi, 10 to the minus 15 meters, and we use natural units, just meaning that everything is measured in energy. Okay, so masses are given in energy, distances are inverse of energies, and so on and so forth. So let's start from the very beginning, and so there was at the beginning of the universe, like 10 to the minus 6 a microsecond. There was the transition between quark matter and hadronic matter. So there was the formation of protons and neutrons, then eventually neutrons decayed. And the way you should look at this is in this way, that the energy was trapped, part of the energy of the universe was trapped in baryons. Okay, so there was a huge amount of energy. And then at that time, what happened was that a great part of this energy was trapped in baryons. So in objects which are of with the radius of about 1 Fermi, okay, so very small objects where the energy of the universe was captured. Okay, so imagine this. It's hard to imagine the Big Bang, I understand, but imagine that there's a huge amount of energy which at certain points is just trapped in this barrier. So the thing is that can we understand what's going on? Not everything. Here, of course, we are not telling about understanding everything, but just understanding what was happening in this time scale here of microseconds. Okay, this is, as my daughter used to say, a vintage view of of what happened in the universe. It's a 1989 cartoon. And so many things happen. Very interesting thing happened here. Formation of galaxies happens here. And so in the quark area, which is this one here, we have this transition between the confined matter made by quarks and gluons to standard hadronic matter. Okay. So can we reproduce it in a lab? Can we really understand it? And in the end, what is really matter made of? Suppose you look at a piece of something with a magnifying lens, like take a piece of iron, and you start to look inside at bigger energies. What's going on here? It's stuck, I think. Yeah, please. Yeah, it's going. Okay.
No,
sure.
question.
Yeah.
Okay, perfect.
Nice. Okay, this. Okay, so no.
So
So you think you understand?
la condivisione.
Da casa non vedo.
Yep. Okay. So magnifying lens for us means using a probe with the higher and higher energy. So you start to resolve what is inside an iron. You see, say, at the micro scale, a lattice, a BCC lattice of atoms. And then you have one single cell, BCC. Then you keep increasing the energy, and then you start to resolve an atom. So we are at the angstrom scale. And there's a very small object here, which is the nucleus. And inside the nucleus, there are protons and neutrons. And inside proton and neutron, there are quarks. Okay. So this is a kind of reverse, okay, of what's been happening during at the beginning of the universe. Okay, where we were starting for quarks and gluons, which were captured, trapped in protons and neutrons, and then eventually heavier atoms were formed much later, thanks to stars, basically. So a way of describing this is thanks to this the QCD phase diagram. So it is description of matter as a function of temperature, of baryonic chemical potential, and the isospin chemical potential. So this tells you how hot is matter. This tells you how dense it is. And this tells you how symmetric or asymmetric it is, whether there are more pure protons than neutrons, okay, inside the matter you're studying, okay? It's called isospin asymmetry because protons and neutrons are in two different states of isospin, by the way. But and what we know here is just that there is a critical temperature here, which separates the hadronic matter, which is here, from something else, which is in this part here. But you don't see any lines, okay? There's no phase transition between, because if we try to increase the temperature, we actually have a crossover between a confined phase where we have hadrons to a deconfined phase where there's a so-called quark-gluon plasma. But to experiments, heavy ion collision, I've seen no phase transition, okay? Actually, there are little doubts that here there is a crossover. As you increase in density, you should eventually get into a compact star, which is a very small stellar object with a radius of the order of 10 kilometers, a mass about the solar mass. So very, very dense objects. And if you go into this direction, you should at a certain point go in a different phase, which is called the meson condensed phase. And we will discuss these three directions here. There are you will certainly see a QCD phase diagram with lines, okay? But there's no experimental evidence of any phase transition up to now, okay? We have only indirect ideas about what's going on. And as I will show in the end, there has been progress, especially in this direction here of the phase diagram, studying very asymmetric matter. So an historical beginning. Why we do all of this? Because we come from basically our ideas come from ancient Greeks. This is Anaximene, who is lived like 500 years before Christ. And the idea is that there is the possibility to describe whatever we have around us, starting by one single component. It's extremely nice description of matter because you just need one single element, which is air, and it is just in different states that you get water, fire, or earth. Extremely grand unification theory. Okay, it's very extreme, just one component. Okay, very nice but wrong. And so what is matter made of? Maybe, this is a better description, our table of elements here. The thing is that there's too many elements now, right? There is copper, there is hydrogen, there's helium, etc. And moreover, the presence of a systematics suggests a substructure, meaning that there are protons, neutrons, and electrons, which are the basic constituents of this. But the protons, neutrons, and electrons are not alone. Okay, we have many of these, and we distinguish them because of their spin. So they have integer spin, so these are bosons, and these are fermions, and we have many of them. There's even more and more of these objects here. But even in this, even if it's less evident than the previous slide, there is some systematics. Look at these four objects here, delta 0, delta minus, delta plus, and delta plus plus. So there are four states which have different charges and the same mass. Okay, 1.2 GeV. So systematics once again at work. Systematics suggests substructure, and this is one of the motivation for the existence of for having proposing the existence of subatomic particles, quarks. Once again, we look at this and say, well, is there any structure in here? Well, it seems so, okay, because there's not just one element, but there's 6 quarks, 6 leptons, and gauge bosons which mediate interaction, plus the Higgs boson. Systematics suggests that maybe there is another substructure that we don't see yet, okay? But we will not discuss this, okay, today. So what are the elements, which compose hadrons? It's quarks, and there's 6 of them, which have fractional charge. 2/3, this is measured as the charge of the positron, so it's a plus 2/3 and minus 1/3. And there are gluons which do not have, there's 8 of them, there is no electric charge. So there's not really one single element, there's plenty of them which are needed to make hadrons. We do not see quarks and gluons because they are confined inside the baryons and mesons. And so we distinguish them in fermions, so the baryons, and the mesons. And so these are typically described as 3 valence quarks plus something which is due to the gluon exchange. Notice one important thing, okay, that the mass of a nucleon is 1 GeV. The mass of up and down quarks is 3 and 5 MeV. So you should not ever think to these objects as a bound state of something, okay? If you have a bound state of something, means that the energy, the mass of this object is less than the mass of its components, okay? Here, the mass of the object is much, much larger than the mass of it. The gluons are massless. Up and down quarks have 2, 5 MeV mass. This object has 1 GeV. Okay, so what we should try to explain is how the hell is that this object has a mass of 1 GeV. Okay, and this means understanding the fundamental theory of strong interactions. Here as well, this guy, which is composed of an anti-up quark and the D quark, so this is a pi minus, has a mass of 135 MeV, which is once again larger than the mass of its component. You should not think of this object as a bound state of something. Okay. The correct way of describing this as a pseudo, actually, Navier-Goldstone bosons. And I will try to explain how they arise in the theory. And then you have these heavy mesons here, which are actually made by heavy objects. And this is a bound state. You can describe this as a bound state, okay? But only this object here. And actually, you can also use non-relativistic theory because the mass of this object is typically very, very large. So to understand pions, which are the basic one of the basic objects, you should first understand the spontaneous symmetry breaking. I know there's plenty of ways of explaining this. This is my own view of spontaneous symmetry breaking. Okay, so suppose you take a square. Okay, this has a symmetry, discrete symmetry group, which is D4. Okay, so you can rotate. There's an axis. Okay, there's symmetry around this axis here, this axis here. You can make rotation. The name of this discrete group is D4. Okay. Now, suppose you want to minimize something like the distance, which is the shortest path joining the vertices. Well, one naive answer would be this one. Okay, I take just the diagonals. Okay, and this doesn't break any symmetry. Okay, this is exactly the same symmetry as before, but this is not the correct answer. The correct answer is this one. Okay, you can show this is true. This is 30 degrees here. So this is the shortest path connecting the 4 points, which has less symmetry than the starting object. So once you have, in particle physics, we use Lagrangians. Okay, when we try to minimize the Lagrangian. Okay, here, suppose you have the Lagrangian, which describes this object here. The minimization gives you a system which is less symmetric than the system you were starting from. Okay, and the minimum made by broken line path has less symmetries than the square. The minimization procedure leads to symmetry breaking. And there are actually not one, but two degenerate minima, which is this one and this one. Okay, and they are related by a discrete transformation. Now, let's get to a continuous group like O2. Once again, we have these 4 points here on a circle now. And once again, the question is, what is the shortest path? And we know the answer now. And we know that also this one is an answer. But now we can make a continuous transformation from one minimum to the other. And the Goldstone boson exactly does this. Allows you to rotate your system from one minimum to the other. So to span all the possible minima of your theory. And since there's no energy barrier, this is this is done at no energy cost. Okay. So I have a system which has a continuous symmetry. I look for the minimum, okay, of this system, like a minimum length connecting the 4 vertices. I find the minimum which has less symmetry than the starting object. I can do a continuous rotation, an O2 rotation, which just means a rotation of this object, to join 2 different minima, in actually many different infinite minima. Okay. So these are massless modes, Navier-Goldstone bonds, connecting different degenerate minima. You already know many examples of this, like phonons in crystals. Okay, so if you start from an homogeneous system where there is the formation of crystal, you have vibration of the crystals, and these are phonons which are massless. Okay, so this is a very nice example of a Navier-Goldstone boson, or in a different object, like in a superfluid, below a critical temperature, there's a breaking of number conservation, and there's a continuous, spontaneous symmetry breaking over continuous symmetry, and you have massless bosons here. Finally, last but not least, pions in quantum chromodynamics, which is the theory which is interaction, arise from the breaking of chiral symmetry. There's and explaining what is chiral symmetry is really not easy. You just have to think, you can think of this in this way. Chiral comes from a Greek word which means a hand, okay? So a chiral symmetric object is an object which is, once it is reflected by mirror, it looks exactly the same. So if I take my hand here, my left hand here, there's a mirror here, I have my right hand here, okay? So they are related by a chiral symmetry, this object here. And then now, of course, if I move them in this direction, for instance, everything is chirally symmetric. The problem comes when I try to rotate this, because if I rotate this in order in this direction, in order to make this guy rotating as this one, so not breaking chiral symmetry, I have to rotate in the opposite side. Okay, so you understand this is related to spin of the particles. Okay, particles which are mirror reflected. Okay, are if you can distinguish them, this means that the chiral symmetry has been broken. Okay, just of course this is not an explanation of this chiral symmetry. I'm just telling you that it's something which is related to a kind of symmetry of nature, which can be broken, which can be explicitly broken or spontaneously broken. Okay, so pions are the Goldstone bosons arising from the breaking of this. This is no more O2. It's a more complicated group here, okay, which is the chiral group SU2 left and SU3 right, which is broken to this subgroup here, okay, but it is exactly as the O2 case, okay. Just that names for you are different here, and there's not just one Goldstone boson. There's three of them, and these are the pions, the three pions. Okay, there are pseudo because these are pseudo because actually chiral symmetry is not an exact symmetry. It's like having you starting from a circle which is not perfect. It's just a tiny distortion of your initial system, and this reflects in the fact that these objects are not massless. So this has nothing to do with the mass of up and down quark scale. Okay, it's just a generation of which depends on the mass of up and down quarks, but plus depends on interactions, and that's the reason why the pion mass arises so large. On the other hand, mesons, heavy mesons, are, you can see, look at them as the bound states of heavy quarks. Okay, so just two objects here strongly interacting, having a mass which is smaller than the masses of the constituent heavy quarks. So this is a double role of mesons, which is very important when we try to probe the QCD phase diagram. So what is the theory which describes all of this? It's called quantum chromodynamics. Chromo means color, okay? So why color? This is once again to do Gell-Mann, okay? The very bright person. And in the 50s, the delta meson, the delta baryon, sorry, was discovered. Okay, as I said before, there's four of them. Okay, so it is technically it's they are eigenstates of 3½ isospin. Okay, four different states. But the thing is that, however, even this single object here is really puzzling because it has a spin which is 3½, meaning that the 3½ quarks are in the same directions. Suppose these are electrons. It's like having in a level 3 electrons which have aligned spin. Okay, so it's impossible. Okay, this is forbidden by the Pauli exclusion principle. Okay, it's not possible to have this state, but it was observed. It was observed in two simultaneously, actually, in two different experiments, and now we certainly know that it exists. So how is that possible to have this object here? To save everything, Gell-Mann. Sorry, it is also another thing. Why these states do not exist? Why up do not form a meson? Okay, why down or up or anti-up do not form a meson? So either the answer is that there's an internal degrees of freedom which is called color, and quarks can come in three different colors. It's just sometimes it is confusing. Okay, using red, green, blue because one has in mind, no real color or something. It's just a weird name given to this internal degree of freedom. He could have been calling anything else, but he decided it was red, green, and blue, and now we all discussed about calling them red, green, and blue. And so we can write now these objects here. We can distinguish a red half quark, a green half quark, and a blue half quark. So they are different, and so we can pair them and forming a state to save Pauli's principle. At the beginning, there was not really, I mean, people were just thinking, okay, it's just, thanks, I mean, it's something which is not real, okay? It's not really related to something that we can observe, it's just a way of saving the theory, you know? Some kitchen, you're cooking your stuff just to get something that you observe in the spectroscopy, so you have been in experiments. And then the answer was, okay, but this, you cannot observe color because all baryons and mesons should be colorless. So it's hidden inside your object. So you're giving a quantum number that I cannot observe just to save your theory, or this is nonsense. But then in the end, we started to believe in this theory because it actually can be formulated as a non-abelian gauge theory. So this simply means that I have, say, an interaction between an up and down quark, an anti-down quark, which is mediated by this gluon, okay? And they can self-interact among them. It's changing color. In the end, I get, by some miracle, an object which is colorless, okay? And the theory which describes all of this is called quantum chromodynamics. It's a gauge theory, which just means that interaction is mediated by gauge bosons, and non-abelian because gluons can interact with themselves. So it's different from electromagnetism because the photon in vacuum cannot interact with itself. Well, it's extremely suppressed, to be more precise. But gluons have all of these vertices here, and that's one of the reasons why this theory is so complicated. But also that allows us to understand the mass of the baryon. So what is inside the baryon? How can we imagine what is inside it? The sum of the masses of the quarks is 1%. So these are the 3 valence quarks which have these springs connecting them. But I have actually an extremely large number of these objects, also virtual objects popping up. So you should think of proton as a blob of energy induced by the strong interactions. Okay, and this has nothing to do with the Higgs mechanism. Okay, people say the Higgs mechanism gives mass to what we have around. That's not true. It's the strong interaction which gives mass to proton and neutrons. It's not the Higgs mechanism. The Higgs mechanism gives this teeny tiny mass to the up and down quark. The proton and neutron have a so large energy because it's a blob of energy captured at the beginning of the universe. And it's always there because this quantum number is conserved. Okay? They cannot escape. We will try to make them escape from them. But in the end, if you start with the proton, you will end with a proton or a neutron. Well, it depends. But okay, it was kept at the beginning of the universe after a microsecond, and it's still there. Okay? You know how fantastic is this theory. Let's try to understand a bit more about this. So electromagnetism, we can also have electromagnetism between up and down quarks, the exchange of photon. Okay, this is a kind of Feynman diagram description. And then we can have, in a strong interaction, exchange of gluons, which actually changes color. An up red quark can become an up green quark. But pretty much at this level, everything is similar. But this is not, as we've seen, the only kind of diagram that we have. Indeed, things become maybe more transparent if we try to understand the nuclear interactions. So this is QED. Okay, I have neutral atoms. So the Coulomb interaction is 1 over r squared. It's pretty strong in inside atoms. Okay, but these are neutral objects, so they in principle shouldn't interact among them unless they are so close that they have van der Waals forces, which scale as r to the 7. Standard nuclear forces can be understood in a similar way. So you have a proton here, or 2 nucleons here, which are far away, so very weakly interacting. As you approach them, there is a polarization of the clouds of pions and other mesons which are around them, which gives us the standard nuclear interactions. But the strong interaction, which you could understand as a kind of van der Waals forces acting between them. Here, there's a strong interactions at work, which just keeps these objects together. Okay? And there's also this extremely interesting thing that in QED, actually increasing the energy scale by which we are probing, so the lensing, the lens we use to see our electrons, tells us that the interactions increases with energy. Here instead, the strong interactions decreases with energy. So this is the running, okay, how the interaction strength changes with energy. So this tells you that actually standard matter is complicated because this is growing. Okay, so this is a non-perturbative and we see also confining theory. But if I look at extremes, so a very energetic scattering, I can use perturbation theory. Or if I use a high energy scale, I can maybe understand better QCD. So it's exactly the opposite of what happens in electrodynamics. These are some numerical results plus some experimental results about the running of the strong coupling. Now it's with distance. So at very short distances, this is called asymptotic freedom. This is 2004 Nobel Prize, Politzer, Gross, and Wilczek. Okay, and here you have a strongly interacting theory when this is approaching 1, and this is a confinement. At a certain point, it's the coupling becomes so strong that it's putting which is impossible to use any kind of perturbation theory. I should try to use something else to understand my theory. Anyway, any theory you should use to describe these objects should be used to describe a confinement. A confinement for a meson simply can be described as this. Suppose you have some meson, so a quark and anti-quark object is a boson. You try to stretch it. At a certain point, it's energetically favored to break it to produce two bosons. And this is possible because there's no conservation number here. You cannot do the same with the baryon. How can we see quarks and gluons? One possibility is using a deep inelastic stretching. So the fact that it's asymptotically free object, their interaction strength is reduced as I increase the energy. So I take a very energetic electron, exchanging a virtual photon with this object here. So it is interacting. It is resolving the objects inside, which are the quarks and gluons, inside the nucleon. So the nature of the object you are sending depends on the probe you use. If you go at very large distances, this is a confined proton neutron. If you have a very energetic probe, you start to see the quark content of this object. Okay. So we can define quarks and gluons as asymptotic ultraviolet states of a proton. This notion is not new. Okay. As we've seen at the very beginning, changing the magnifying lens, the nature of the object I was seeing was changing. Okay. So a piece of iron becomes a BCC lattice, a cell, and an atom, and a quark inside. This is just doing the same thing, but just changing the energy of the probe we have here. Now, can we liberate these quarks? So they've been trapped, no? After 1 microsecond after the Big Bang. Can we liberate these guys? We can try different things. We can heat matter, so going along this direction here, maybe ions. We can compress it, okay, to reach a 9 energy scale in this direction here, or we can change their composition going along this direction here. So let's start from heating, okay? So going in this direction of the QCD phase diagram. This is done in a relativistic heavy-ion collision. It's just a cartoon of what's going on. So you have these two heavy nuclei. This can be gold, or can be lead, as relativistic energy scattering, producing something at t = 0, which is really hard to describe. And then these objects fly away, and what they leave here is an expanding hot plasma, okay? And which has a very little baryon number. So there is an equal number of baryons and antibaryons, basically, in this object here. So this is just, producing an extremely high energy scale because we want to go to see the theory where the right degrees of freedom are quarks and gluons. Okay, just a way to reaching a high energy scale. There's a problem, however, that if I have a thermodynamic description of hadrons, it should include all possible states. Okay, so there are these objects we have seen before and many others. And that's the experimental observation that increasing the temperature, the number of possible particles grows exponentially. So as I increase the temperature, suppose you're increasing the temperature, you are heating a proton or a heavy ion, okay? You're heating it. What pops up are more and more states, okay? Not only this one, but more and more than this. And then Hagedorn, a few years ago, came up with this statistical bootstrap idea that the exponential growth of states implies a limiting temperature for hadronic matter. Very roughly, the idea is that close to Tc, putting energy into the system increases the number of particles, not the temperature. So I cannot heat hadronic matter above a certain temperature. If I try to do that, I do not increase T, I just increase the multiplicity of the objects I'm producing. So the number of the objects I'm producing. But there was a caveat that these particles in Hagedorn idea were assumed to be point-like objects. This is true for an electron as an example, but it's not true for a baryon. It has a radius. And this was already noticed by Pomeranchuk. It seems trivial now, okay, but at the beginning was not at all clear that a proton was not a point-like object. Now we know that it's a radius of 1 Fermi. So Pomeranchuk said, okay, but the hadron must have, each hadron should have its own volume to exist. In a finite volume, there must be a finite number of particles. Otherwise, they start to overlap. And then this suggests, so Cabibbo and Parisi, a Nobel Prize and World B Nobel Prize, suggested that the observed exponential spectrum is connected to a system of a different phase of the vacuum in which quarks are not confined. And to my knowledge, this is the first time that the QCD phase diagram was proposed. So in a schematic phase diagram, as they say correctly, so in phase 1, quarks are confined. Here, quarks are liberated. And close to the phase transition, there is a kind of critical opalescence of hadrons. So like in the second order phase transition, you have that any length scale becomes relevant. So it's an opalescence. And the opalescence here is due to the population of hadrons. But that doesn't mean that I cannot go above this temperature. It's just that I have to change my degrees of freedom. The important lesson is that close to TC, which is the limiting temperature of confined hadronic matter, resonances play a crucial role. And TC is the temperature which you get if you insist only to describe baryonic and hadronic matter in terms of confined objects. Okay. Notice that the critical temperature is order of m pi. Okay, so it's all of these scales are, all of them are close by. There's a reason because they are connected with fundamental properties of QCD. So if I increase the temperature, I should get in the phase which is named the quark-gluon plasma. So the confined phase of quarks and gluons. This is very, I mean, it's just a cartoon which will not run, of course, because this is PDF. But what I'm doing here is just increasing the temperature, so increasing the number of states, like in Hagedorn. Okay, so increase the temperature. I do not increasing the real temperature, putting energy in the system, not increasing the temperature, increasing the multiplicity of the objects, and they start to overlap. So the quarks which are here start to percolate. Okay, and this is a way of understanding the confinement. So there are two nucleons now, they touch, they overlap, and the quarks which are here can go there. Now you put more and more of these objects here, and you form a blob of matter in which quarks and gluons can move. Okay. How can we probe this? Using, for instance, heavy quarks. This is, so, as I said, just two heavy quarks, so they have a mass, say, of order GeV, even more, okay, which form a bound state. I can really describe this with a non-relativistic model. Just this is called Cornell potential, but it's just a potential which you can use to reproduce spectroscopy. And increasing T or the density, I should describe this object in a medium. Okay, and there are two kinds of medium effects. One is the biscreening, and the other one is Landau damping. Let's try to understand what we mean by that. So these objects, you can calculate the radius of these objects of the 0.5 Fermi. Okay, it's a very, very compact object. Now I increase the temperature and I stay below TC. So my resonances here pop up. Okay, these are mesons which are popping up. And I can also increase the density of baryons. And so protons and neutrons pop up. Okay, and so they start to disturb the system. But the thing is that this picture is not in scale, because actually this is 0.5 Fermi, and this is 1 Fermi. So they cannot really alter the interaction between these two heavy quarks. In order to do that, I have to go above TC, in which now my correct degree of freedom are quarks and gluons. I mean, depicting only quarks here by these black dots here. They start to interfere with the field, which connects Q and Q bar, quarks, and producing an Yukawa potential among them. So there's a screening of the interaction. Okay, pretty much as happening in condensed matter physics. Now, if the distance between these objects is larger than the bi-screening length, the potential becomes so low that this system is broken. Okay, so I have dissociation. But this does not happen at TC, but a temperature larger than TC. So I have a thermometer. I can study the dissociation of these objects here and measure the temperature, measure in quotes, the temperature or even the density of my system, because we are expecting this to happen in hot medium or in dense medium. Unfortunately, this is what proposed by Matsu and Satz in 1986. But this is not the end of the story, because actually, when you have a thermal medium, there's no strictly stationary bound state. There is. Yep. Yes.
So you have a quantum physics.
Yeah. Right. So the thing is, if I have a thermal medium of quarks, or in general thermal medium, I really never have a bound state, okay? Because I have some distribution, a thermal distribution, in which there's always, particles which are extremely energetic, and sooner or later, one of these will hit this object here, and we determine the dissociation of this bound state. And this is Landau damping explained really in the easiest way possible. Okay, so what happens is that if you try to write down the Schrödinger equation governing these objects here, you find that you have to add an imaginary part of the potential. Okay, because there's no conservation of energy anymore, because it takes energy from the thermal bath, which is surrounding it. This is not weird. Something we should know, because this is exactly what happens if you have oxygen in a thermal bath. So there's some photon which hits oxygen, molecular oxygen, and produces, for instance, 2 atoms of oxygen. So it's not something new. I mean, Landau damping is a very known effect. And the same should happen here. So another way of understanding whether there's a formation of a quark-gluon plasma. Okay, there's no smoking gun all over this. Okay, it's just that we have observation of these effects, which help us to understand that something is happening in our system, which is compatible with the description in terms of a quark-gluon plasma. So what happens instead if I increase the matter density? So now I move, previously I was moving along this direction here, now we're moving along this direction here. Now, once again, I get problems. Why? Because suppose I take the densest stellar objects known, which are neutron stars. They have a mass which is in between 1 and 2 solar masses, very compact in a radius of about 10 kilometers, pretty cold as compared to the typical temperature of strong interaction, which is MEV. Okay, this is at most keV for sufficiently old neutron stars. The thing is that the traditional neutron star is an object which in its interior has neutron, protons, electrons, and muons, so standard, somehow standard matter. If I try to do something different, and somehow consistently I should do that, I find many different possibilities. Okay, and that's and one of the reasons is that I have no strict control on the theory, because I can exactly address QCD if I am in the perturbative regime, which happens at extremely high energy scales. In between, I have to use some model of it. So a neutron star has a standard crust, which is standard in the sense that it's made by ions and electrons, and which becomes a neutron rich as they get inside. But I can have also the production of, you see the delta pops up everywhere. It's again here in this model. These are instead of hyperons, other particles, and or I can have the confinement in the center, where I have up and down and strange quarks, okay? Or I can have other phases which are called pion condensation and kaon condensation, and we shall be discussing a bit this in the end. Why should that happen? Well, for many reasons. And why should I have the confined quark matter? Because the density in these objects can be so large that it is larger than the density I have at the center of heavy nuclei. So once again, it's telling me that these nuclei are starting to overlap. And once again, quarks are starting to percolate. Okay, so is this geometrical description enough? No, of course. Okay, it's not enough for telling you that this is what's going on here. Okay, you should have a theory, a good theory for describing it. And so can we somehow probe this on the Earth? Well, somehow we can probe up to certain densities. These are the typical densities where these weird nuclei are not so weird, actually. This is zinc 80 observed on the Earth. This is just the result of calculation. And but basically we have to stop around this point. Now, I mean, this is pretty old, 94. You can do maybe slightly better now. But the thing is that it's very hard to get cold nuclear matter with very high densities. Okay, and this point here is called the neutron drip because it's the point in which the density is so high that the neutrons which are inside nuclei are getting outside your lattice of ions. Notice that there's many electrons here, which is a kind of important thing in describing this kind of matter. So let's try to figure out, this is just a cartoon, okay, of what's going on. So this in this plot you have here a cartoon description of matter inside a neutron star. This is the part of neutron star. This is the atmosphere, which is really teeny tiny atmosphere on top of a neutron star. This is the outer part of the neutron star, which is called outer crust, inner crust. There's the core in the very center of the star. And this is the guy we've seen before. Now it's not more a function of the energy of the particle, but of the chemical potential, which tells you the typical energy scale of your system. And these are the right degrees of freedom you should use. So here instead is the density. So we have an outer part which is pretty low density. As we get inside the neutron star, larger and larger densities. Here is an important point, which is neutron drip. So these are my atoms, the nuclei, and there's a drip of neutrons which get outside of the outside of heavy nuclei. And here instead I have the point in which I'm crossing between the inner crust and the core, where you have a soup of neutrons and protons. So all of my nuclei have been are forming a sea of neutrons and protons. This is a very simplified description, but the important thing to keep in mind is what are the correct degrees of freedom here. Now, what happens here that maybe this can go down to the core, or maybe I have something similar to what is happening here. So here I have a neutron drip, so neutrons getting outside heavy nuclei. I can have a quark drip here. So quarks start to move in between nucleons. And finally, in extreme densities, which cannot be reached probably in the core of neutron stars, I have a quark soup, a quark and gluon soup. So this is an effective way of probing the confinement. And the picture is complicated by the fact that even if you are the confined quarks and gluons, so you have now a point-like object, which is a quark, and a melted baryon here. But this object here still can pair with the others. And this gives a very interesting phenomenon, which we call color superconductivity. So you have a liquid of quarks in which you form correlated pairs of quarks. And this is pretty similar to what happens to superconductor, in which you have correlated pairs of electrons forming Cooper pairs. And the interesting thing is that the typical correlation length of these objects can be larger than the typical distance of these between these two quarks. Okay, but this is not new at all, because it is if you look at the kind of interaction you have these two objects here, this is can be pretty similar to the kind of interaction you have between electrons when you form a superconductor. The only thing is that it's not an electromagnetic superconductor, it is a color superconductor, okay? And the theory, I have to mention this because one of the most favored states, which is called the color favor locking phase, it's a phase in which you remember we have up and down quarks with the three different colors. They can all pair. So there's a global collective behavior of this system, which produces a phase which has a very large energy gain as compared to the Fermi liquid, standard Fermi liquid description. And so they form Cooper pairs, and this can have important effect on the, for example, the cooling of these stellar objects. And there's a spontaneous symmetry breaking of gluons. They get the mass that becomes a core superconductor, and there's also the breaking of a global symmetry, like the O2 we started with, and so the system is superfluid. Plus, I mean, there's a review I've written with this gentleman here, in which we collected papers on possibly inhomogeneous phases inside compact stars. Last but not least, we move in this direction here. So we change the composition of matter. Yes.
Just quickly.
Well, well, okay, it's a no, no, it can be huge. Okay, the gap parameter, for instance, can be hundreds of MeV, for instance.
But then
Yeah, can be much larger than this. Okay. Yeah. Plus, there's also the thing that here the interactions. Okay, it's complicated. Okay. Okay. Now we move along this direction here finally, and in the direction of pion condensation. So you very well know that pions are unstable particles. They decay in leptons. Because electricity conservation, they prefer to decay in muons, but in any case, I mean, charged pions decay in leptons in neutrinos, weak decay process. So if I depict here the energy levels of pions and electrons, it's just that this state here is not populated and this state is populated. But if I increase the number of electrons in my system because they are trapped, these energy levels goes up. And they can eventually have a state in which the chemical potential, so the energy level of electrons, is equal to the mass of the pion. So pions can no more decay in muons or in electrons. Okay, so they are Pauli. We say they are Pauli blocked. If I look at the energy spectrum, we see that when mu I, so this chemical potential equals the mass of the pion, we get this dispersion law, and massless mode appears. And you remember that massless mode appears when there is a spontaneous symmetry breaking. So this system is becoming a superfluid. Okay. And this is the phase diagram. Just here I'm plotting mu I and mu S. This is telling you how many strange quarks you have. Here you're telling you whether you have more up or down quarks. And so I cross mu I equal m pi, and I get a superfluid. Actually, it's a superconductor, but let's forget about the fact that it's a charged object. A superfluid of pions, or I have a superfluid of negative pions, or I have a superfluid of kaons, which are other mesons. And so asymptotic mu I and mu S matter should be deconfined in a rather unusual way. It's not just that you're increasing the density. You're actually altering the composition of matter, forcing it in a state in which there's much more neutrons, say, than protons. But that's actually what's happening in a neutron star. That's the very name of neutron star is telling you there are many more neutrons than protons. And indeed, you remember there was a plot, a cartoon of the interior of a neutron star. There was a region where there was pion condensation. So maybe in that region, we can actually produce one of these phases here. The interesting thing is that in this case, you can do calculations using a numerical simulation of QCD, which is called Lattice QCD, which I certainly not explain what it is. I just am telling you that you can put QCD on a lattice, so discretize the distances and run a numerical code which gives you the favored phase as a function of temperature and asymmetry of matter. So these are some models which are called chiral perturbation theory and NGL. And this is the result of Lattice QCD. So they kind of agree, okay, we can improve this. We can certainly improve also this one. We kind of believe that it's going like this. So this is a normal phase. This is a pion condensate phase. And there's a quark-gluon plasma on the top of it. How does it match with the QCD phase diagram? First, before going to that, let me tell you that, so now we can distinguish the phases of hadronic matter by the condensate, which are these objects that break symmetries. Chiral condensate, diquark condensate, which produces color superconductor, pion condensate, which produces meson condensation. Quark-gluon plasma, not condensate, okay? Well, there can be gluon condensate, but it's not okay. They're not important for us. So any quark condensate breaks or locks the symmetries of QCD. Okay, we have seen what spontaneous symmetry breaking means. Locking is just the fact that some symmetries are just mixed. Okay, this is what happens in the standard model, by the way. So here is my personal final picture of the QCD phase diagram. So we have an hadron gas here. The hadron gas can be proved by heating matter in a relativistic ion collision, and we have a crossover. We expect that this is a transition line that we have not seen so far. We have not seen any critical point here so far, which goes in a color superconducting phase, where this particular condensate is responsible of the pertinent spontaneous symmetry breaking. Here, we have lattice QCD and numerical simulations, which basically agree to give us a second order phase transition. And we have a pion condensate phase, where we have another condensate which spontaneously breaks the symmetries of QCD. So the only line which I would trust in this is this line here, okay? And of course, the crossover, which is experimentally observed and also produced in numerical simulations. Anything else up to now is just question marks, like quarks, question marks, okay? The crazy of these two words. And so these are my conclusions. Nucleons, you should think of nucleons as something which is being created soon after the Big Bang, microseconds after the Big Bang. And it is very hard to explore, okay? But extreme conditions help because of asymptotic freedom. So help us to produce a matter in which quarks and gluons are the right degrees of freedom, and in extreme densities, the interaction is perturbative. But there is a richness of phase, which is connected to a rich, very rich particle spectrum. Okay, thanks a lot for your attention.